In this lesson, we're starting a unit on angle measure, and then we will move into right triangle trig, and then we will move into angles around the circle, and do a lot of the basic trig work that you learned last year in Algebra 2 trig, and so most of this unit will be review. We're going to start off in this lesson with some definitions, and our angle definitions. The very basic thing is defining the different parts of the angle and our degree measure, positive and negative. So here we have our standard angle, and one of the sides we would call the initial side. When we go to the coordinate axis, the initial side is typically on the positive x-axis. So here's our initial side. And then the other side is called the terminal side. So the initial side is typically stationary, and the terminal side is the one that's going around. We typically use theta to denote our angle, and when we start with the initial side and we move counterclockwise, that is a positive direction. So moving counterclockwise is going to be considered a positive angle measurement. However, we don't have to move counterclockwise. We can go around with our initial, or again locking in our initial side and move into our terminal side. We can move clockwise as well. That's just going to be a negative angle measurement. So as you start from the initial and move to the terminal in a clockwise rotation, we consider that a negative measurement value. So up until Algebra 2 trig, you have measured angles in degrees and minutes, more or less, usually degrees. But we want to talk about another way of measuring angle measurement. So here we have our basic circle, and if we think about it, I looked up one time the origin of degree measurements. We know there are 360 degrees. If we go all the way around this circle, completely around, we would be going 360 degrees. So the origins of that, do you ever think, I'm sure you haven't thought about why there are 360 degrees in a circle? I mean, why not 100 degrees in a circle? Make it nice and even, or 1,000 degrees, or whatever. And I don't think anyone knows the exact origin of doing this, but it's attributed to the ancient Babylonians. This is one story. And the ancient Babylonians loved the number 6, and 360 just ends up being a very convenient number. It's divisible by 6, it's divisible by 12, it's divisible by 2 and 4 and 10, and so many different measurements we can use with the number 360. So the taking a circle and dividing it up into 360 little bits, and then dividing up those bits into 60 little minutes in between, that is actually, we believe, an arbitrary decision. There's no real meaning behind taking a circle and dividing it up into 360 parts. It just happens to be convenient. It happens to be convenient if you're measuring angle measures using a protractor and whatever, but it's not very convenient if we're trying to relate something on the circle to the actual angle measurement itself. So in order to do that, we need to come up with a different way of measuring that central angle in a circle. So here's what was created. If you think about the circle and the formula for the circumference of a circle is equal to 2 pi times the radius. And the circumference, remember, is the distance all the way around the edge of that circle. So if I can come up with something to relate this distance to the actual angle measure, that's going to be a lot more useful in application problems and other types of, area problems or arc length problems or anything like that. So if we think about this, if I were to have a central angle, and if I went halfway around the circle, well, I know that creates a line, so my degree measurement is going to be 180 degrees. Okay. Well, if I actually calculated the distance around, so we have a radius r, and let's assume this is a unit circle, so my radius is going to be 1. If I were to actually calculate the distance around that with a radius of 1 going halfway around the circle, the circumference is going to be 1/2 the entire distance around the circle times 2 times pi times that radius. So halfway around the circle in a unit circle, the 1/2 is going to reduce with the 2 pi, and the circumference is actually equal to pi. So what we want to come up with is a definition for an angle measure that basically says whatever this angle measure is, I can directly relate it to the arc length that it creates. And that's the origin of radian measure, because the radian measure in a unit circle, this, what we call a radian angle measurement, is going to be equal to the length of the arc that it creates. What this lets me do is directly relate an angle measurement to a distance. That is not something we could do with degree measurement. Remember, degree measurement is rather arbitrary. It's just taking a circle and chopping it up into 360 little bits. Radian measure proves to be much more useful to us in science applications and physics and modeling applications. So that's why we want to get really used to working in radian measure. So we'll start next by writing down the definition of radian measure. And we start with this statement. In a unit circle, that means I have a radius of 1. The measure of the central angle in radians, and remember the central angle is the angle that's subtended in the middle of a circle. The central angle in radians is equal to the length of the arc it creates. So in a unit circle, that means I have a radius of 1. The measure of the central angle as defined in radians is equal to the length of the arc it creates. So we're going to use this, and we're going to work a little bit on converting between degrees and radians, and then we'll do a few more definitions. So let's talk about how to convert between degrees and radians, and there's just a couple things you need to know. From evaluating the length of half the distance around the circle in the unit circle, which we talked about on the previous, a little bit ago, we know that there are pi radians in 180 degrees. Now, pi is just a number. It's 3.1415, whatever. There are exactly pi radians in 180 degrees. So I believe the way you learned last year to convert from one to the other is to use a proportion. You could use this as a scale factor if you're used to scale factors, but I think what you're used to is setting up a proportion. Therefore, you can solve for either one. So the proportion is going to look like this. If you have degrees, then that's over 180, and that's equal to radians over pi. This is useful because depending on what you have and what you're trying to solve, you can use the same proportion each time. If you have degrees and want to go to radians, then your x value would be here, and your numerical value would be there, and then you would cross multiply and solve. The same with if you're starting with radians and need to go to degrees. You could also set it up with pi over 180 and radians over degrees. It would be the equivalent proportion. So here's an example to show you what we're going to do. We want to convert 65 degrees to radians. The first explanation says we want to leave exact, meaning we can leave pi right where it is, which makes it pretty easy, and then we want to round to 4 decimal places. So degrees over 180 is equal to what I'm trying to find over pi. When you cross multiply, you get 65 pi over 180, and if I reduce that, it ends up being 13 pi over 36. That's the exact answer because we don't multiply pi out, we just leave it as it is. To round to 4 decimal places, all I do is I put that in the calculator, and I end up with 1.1345 radians. So radian measure does not always have to be in terms of pi. Okay, radian measure is just a number, and it's usually a number, it's going to be a number between 0 and about 6 or so. but it is just a number. Now, if I want to convert from a radian measure that's in terms of pi back to degrees, remember, there are 180 degrees in pi radians. So an easy way to do this is just replace the pi with 180. And then you're not dealing with complex fractions or anything like that. That's a really simple way to do it because you know there are 180 degrees in pi radians as a conversion, and you end up with 105 degrees. So that's not too bad. So we have just a few more definitions, and then we'll be finished with this. And the first one is an angle in standard position. This is when we get to the XY plane. So it's drawn in the XY coordinate plane. The initial side is on the positive x-axis and the vertex is at the origin. Basically, we're taking our angle and we are centering it at the origin. So an angle in standard position would look like that. Again, positive would be counterclockwise, negative would be clockwise. And then we will finish up by talking about coterminal angles. So coterminal angles share the same terminal side, but their angle measurements might be different. They can be different by a multiple of 360 or 2 pi if you're in radians. So these angles can be found by adding or subtracting multiples of 360 degrees or 2 pi. So we're going to finish with this example and then we'll work some more in class. Find an angle theta where theta is going to be between 0 and 360 degrees is coterminal with 1050. 1050 is larger, obviously, than 360. So we'll take the 1050 and we will keep subtracting 360 from it. If I do that once, I end up with 690. I'm still larger than 360, so I go again, and I end up with 330 degrees. Once I'm between 0 and 360, I'm done. So my answer is 330 degrees. Again, we're going to do this more in class and practice converting from radians to degrees and back again.